Okay, in this video we're going to look at redox equilibria. So I've put the most basic sort of battery as such, what you'll use up there. So it's the zinc and copper one. We'll talk through what's actually happening in it, some of the properties which the salt bridge and such must have, and then we'll come on to looking at this table here. So first off, the basic things. As you can see here, we've got two electrodes in there. So we've got a zinc electrode and a copper electrode. We've got some solutions here, copper sulfate and zinc sulfate. They are both 1 molar. We'll look at the standard conditions in a second as well with the hydrogen electrode. And linking them here, we've got a salt bridge. So the salt bridge can be any sort of the group 1 nitrates or the chlorides, so sodium nitrate, potassium nitrate, potassium chloride, just whatever your favourite chemical is with that really. Their main purpose is, just as we can see across here, it's to transfer ions, because as we'll come on to, some of these get used up and we need to keep the charge in these solutions constant. So as you can see here, when the copper 2 plus moves out, the K plus will move in to replace the positive charge lost. And ditto across here, when zinc 2 plus forms, then the nitrate ion coming in there, that cancels out that extra positive charge. Now we don't use a metal wire for this bridge. The reason why is it would just end up setting up its own electrode system in there. You could have it losing or gaining electrons. So this is why you've got the salt bridge instead. Obviously the other property what it must have is the fact that it's going to be dipping in these solutions. It mustn't react with them as well. Now up here you can see we've got a voltmeter. What that's doing is it's basically just acting as a brick wall, and it's measuring sort of how strongly the electrons are pushing against this. So it links in a bit with the physics terms, voltage, potential difference, things like that. Depending on whether or not you're doing physics, you might fully understand those. It's just basically looking at how much the electrons are pushing against this. So we could replace that with a little bulb, and obviously the electrons moving around would just light up the bulb instead. Now for what's actually happening at each electrode, then this is what I use to help remember it, red cat. So reduction occurs at the cathode, that's what that's there for. I cannot draw a cat. They either end up looking like rats or mythological creatures with 8-foot teeth. So here is one I painted earlier. And hopefully that helps you remember it then. So reduction at the cathode. So you'll be given a table like this in the exam for when you come on to doing these calculations, or when you need to actually write the cell in its standard form. We'll do one of those in a second. Now it's the most positive number which will gain the electrons. So what these numbers for is they are taken against the standard hydrogen, which we'll look at in a second, and it basically just determines if they are stronger or weaker than it, the hydrogen are taking or losing the electrons from it. So copper here has got a value of plus 0.34. So what that means is copper 2 plus will take electrons from the hydrogen electrode, whereas down here the fact that the zinc 2 plus has got a negative value, it wouldn't. So if I put these solutions together, what will actually happen is the more positive one oxidizes the one below it. So the copper 2 plus will take electrons and turn into copper. So it is classed as an oxidizing agent. An oxidizing agent takes electrons. Notice I did not say a pair of electrons there. I know it is a pair here, but you can quite easily take 1, 3, 5, 7 electrons depending on what chemical you're actually using. So an oxidizing agent takes electrons. So obviously the copper 2 plus is reduced because it's taking them, it's gained the electrons, turned into this. So the copper electrode across here would actually become fatter as time goes on, because the copper 2 plus would take electrons that were coming round and it would deposit on this electrode as extra copper. So the size of this would build up. It would be vice versa for the zinc one. So down here, the zinc metal here would actually have to lose electrons. So the zinc is acting as a reducing agent. So if you ever asked to name the reducing agent, it is not the zinc 2 plus, because the zinc 2 plus does not lose the electrons. It is the zinc metal which loses the electrons. So the metal, the zinc, turns into extra zinc 2 plus, and the electrons flow round and obviously come here where the electrodes, so both of these must be able to conduct electricity, and the copper 2 plus picks them up. So if I was to combine these into a full equation, obviously this takes 2 electrons, this releases 2 electrons, so it would just be copper 2 plus zinc goes to copper as a solid plus the zinc 2 plus in its aqueous form. So I'll show you how to write the cell properly, and we'll do a calculation to work out the total voltage now. Okay, so again I've shown the numbers up here. Remember in the exam as well, they'll probably not be nice and have them listed most positive to most negative as they're normally shown in books. So the most positive one, that is the best oxidizing agent. So the copper 2 plus here is a really good oxidizing agent in this table, whereas the zinc, this is your good reducing agent. So the zinc obviously acts as a reducing agent, loses electrons, and it causes the copper 2 plus to be reduced and to gain them. So in order to work out the AMF of this cell, then this is how it expects it to be written, as it's usually asked in the exam, sort of for the more simple ones like this. Sometimes you get ones where the phase doesn't change, so I'll say how to write that in a second. Then as we can see here, you just write it out in sort of the oil rig form. So put your oxidation first and your reduction second. So the zinc is being oxidized, it's going from zinc to zinc 2 plus, so across here, and the copper 2 plus, this is being reduced, turning from the 2 plus to the copper metal. Now the straight line here represents a phase change, because as we can see, we're going from the aqueous form to the solid form, and ditto across there, going from the solid to the aqueous. So if you're changing from, say, solid to aqueous or aqueous to gas, things like that, then you need the straight line. If you're dealing with a solution, say, iron 2 plus and iron 3 plus, where you've got a platinum electrode in there, show an example of that in a minute with the hydrogen electrode system, then you would just have a comma rather than a straight line. What I would say to be careful of is if ever you're unsure about which one to be using, use the straight line. The exam tends to be far more generous towards allowing that, even in systems where it's not strictly correct, than if you put a comma when there should actually be a line like this. The double line here, that represents the salt bridge between them, so it's sort of breaking up the two half cell systems there. Now in order to work out the EMF of this full battery, then all you do is the right hand side take away the left hand side. So whatever's being reduced, as we can see up here, so it's going to be your more positive number, take away the less positive number. So the 0.34 take away minus 0.76. So even though you're going backwards, don't flip the number there. The actual, because of the way you're doing right minus left here, it takes it into account anyways. So the 0.34 take away minus 0.76, then this battery is going to have an AMF of 1.1 volts. Now as long as it's above sort of 0.4 volts, then the battery will work. So if ever questions are asking you, would this reaction be feasible in terms of generating a current, then all you are looking for is trying to get a positive number above 0.4. If you've got that, then it will work. If it's negative, it will not. Okay, so we've got the standard hydrogen electrode here. Now what this is useful for is for getting these values here. So if we just looked at a half cell of the copper sulfate and copper metal sitting in there, we couldn't really determine which way it would go in terms of the equilibria about either taking electrons or releasing electrons. We need to compare it against something. So everything is compared against this. or again sometimes secondary electrodes which have already been compared against that, because this is a bit of a hassle to set up at times. So as we can see down here, the H plus taking 2 electrons, turning it into H2. By definition, that is given a value of 0. So if you're asking in exams, why does H plus have a voltage value of 0? Just say by definition. It's set as the value of 0 and everything else is compared against the strength of this. So copper 2 plus taking 2 electrons, the fact it's got a positive value just tells me that it is better than the hydrogen ions at taking electrons. So quick talk through the setup of this. As you can see, same as before, the copper electrode dipped in a 1 molar copper sulfate solution. We've got the salt bridge here, so again potassium chloride, something like that. Now we need the platinum electrode across here. Why platinum? Well, 1, because it's inert, so it's not going to react with anything, and 2, because it conducts electricity. So we need this in half cells where there's no actual metal present. We need a surface where the electrons can actually exchange between these things. So either A, the hydrogen releasing the electrons, or B, the hydrogen ions taking electrons, depending on what your other half cell is. So in this case, the fact that the value here is positive, what it tells me is that copper 2 plus is better at taking electrons than the hydrogen ions. So because of that, when the copper 2 plus takes the electrons, something must release them. So the hydrogen gas which comes in here is forced to go the other way. It's oxidized. So this is a better oxidizing agent. This therefore is acting as the reducing agent. So the hydrogen turns into hydrogen ions and releases electrons. So the electrons float around this way, and in this instant this is the cathode. So remember, red cat, reduction occurs at the cathode. If I'd used, say, the zinc which you saw before, which had a negative value, then the electrons would be flowing this way, and it would be the H plus taking electrons turning into H2, and it would be this side which would be the cathode instead. So remember, red cat there to help you get it. Now these are done under standard conditions, so I'll quickly write out the cell needs proper form. Okay, so the half cells combined here, so this is what it would look like for a full sort of written out cell for the standard hydrogen electrode compared with the solution of copper 2 plus and the copper electrode there. So again, it's just the standard oil rig form. As you can see across here though, we've got the platinum electrode, so you always show that on the outside. Straight line there because obviously there's a phase change between the metal and the actual gas, and also a phase change between the gas and the aqueous solution of acid there. Now, in terms of why we use standard conditions, so why we use the 1 molar solution at 298 Kelvin and 100 kilopascals. If you think about standard equilibria, if you increase the concentration of the copper sulfate there, if you increase this, then the system obviously wants to oppose that, it wants to get it back down, so it'll push it to the right to increase the amount of copper solid. In pushing it to the right, then you need more electrons. So the copper 2 plus would effectively become more hungry for the electrons. It would push more to the right, and you would end up increasing this number. So it wouldn't really be a fair comparison if you say compared a 10 molar solution of copper sulfate against a half molar solution of some other ion. So that's why they're all taken as a standard 1 molar in the comparison. Now, why the temperature is used at 298 Kelvin? As the cells move in the forward direction, so as this sort of reacts with the hydrogen, the copper 2 plus turns into the copper and the hydrogen turns into the hydrogen ions, then going in the forward reaction, so this cell here basically, as it works, it tends to be exothermic. So in an exothermic reaction, if you increase the temperature, then you'll actually be decreasing the battery's efficiency. So the voltage wouldn't actually be 0.34, what you would get off at a high temperature. It would actually be less because it would be trying to push backwards to cool itself down. So if I wanted to get a higher voltage, what I should actually do is this cell, do it under a low temperature, and you would actually get a higher one then. But again, for comparisons between everything, if you want to compare the copper 2 plus to zinc 2 plus, then we use a standard temperature. And obviously same for atmospheric pressure in there. I've shown how the cell would look if zinc was used. So obviously in the case of zinc, if you remember, the number for that was negative 0.76. So the zinc in that case actually loses the electrons, and it's the hydrogen ions which take the electrons and turn back into the hydrogen gas. And again, platinum electrode on the outside there, because obviously neither of these are metals. We need some surface where the electrons can be exchanged. Just to sort of finish it off, here's an example with where the phase doesn't change. So when we've got both the iron 2 plus and the 3 plus there. So in this example, obviously it's being oxidized, it's losing the electrons going from the 2 plus to the 3 plus. But as you can see there, the comma, because they are both in the aqueous state. So what I'll do now is I'll go through a few examples of the different types of batteries and the fuel cells. So obviously the non-rechargeable battery, the rechargeable, and the fuel cell. Okay, so this is your standard non-rechargeable zinc battery. And as you can see there, nice little picture showing you sort of how, well, it's a bit of simplification of some of the chemicals in there. But as you can see, we tend to have a zinc coating here, sometimes steel around it just to give it a bit further strength. You've got a zinc chloride paste, porous separator, and then manganese oxide paste in there. You've got a carbon rod there, just acting similar to platinum in reality. It's just acting as a conducting surface. Obviously just for the electricity moving round and letting the manganese oxide pick the electrons up from it. So I've shown the two equations across here. So as we can see, the manganese oxide, a value of plus 0.74, whereas this reaction here, negative 0.76. So the manganese oxide will oxidize zinc. It causes the zinc to lose electrons and turn into zinc 2 plus. So this is acting as an oxidizing agent. It is taking electrons. So if I want to work out the voltage of the cell, then obviously just the more positive take away the less positive. So as you can see here, we come out with a value of 1.5 volts for the electromagnetic force there. Now, in terms of what will happen to this battery over time, now the porous separator effectively just acts as a salt bridge. The main property which it must have is just ions must be able to pass over, because obviously we need to keep the charges in here fairly constant, otherwise the electrons won't flow around. Now as the zinc turns into the zinc 2 plus, then this outer coating will wear away. So it's why batteries start to leak after a period of time, because obviously it just gets eaten away here. You lose your zinc metal, keeping all the paste in, and that's why it starts to spill out. So the zinc 2 plus would be what's crossing into the porous, well, crossing across the porous separator there, just to keep the charges constant. And in terms of what will happen to the EMF over a period of time, as we can see here, it does decrease. The reason why is just we are going to run out of zinc metal there. So obviously there's going to be less of it able to transfer electrons to feed this reaction. So in terms of an overall reaction, it's going to be reactant here plus reactant here goes to product, product. Obviously, if we wanted to combine them into a full equation, we would need to double everything on this line, because this needs 1 electron, whereas this releases 2 electrons. So obviously some problems with the non-rechargeable cells like this. They do just get used up, nice, cheap, easy to make, but then they just get dumped in landfills. So there's a bit of an environmental problem there. So just waste disposal really. So we'll look at the rechargeable batteries in a second. Obviously the advantage of those is less of them end up in landfills. Okay, so two equations here which we can link together into a rechargeable battery. The one which was usually looked at is the lead sulfate ones. Just I've got an exam paper open next to me, so we'll just talk through this one. So as you can see here, we've got the cadmium, which is acting as a reducing agent because its value is more negative, so it's going this way, releasing the electrons. Whereas across here, this reaction is proceeding forward, more positive value, so it's taking in the electrons. If you wanted to combine them into a full equation, just remember to double this line because we need 2 electrons. Obviously, we need to get the electrons to balance out. So as you can see here, we would get a voltage of 1.4 volts from this cell. Now, in order to actually recharge it, what we need to do is to provide basically a pushback of electrons. We need a voltage which is bigger than this in order to cause the reactions to reverse. So what would happen is the cadmium hydroxide across here would end up taking in electrons, turning back into cadmium, and likewise this reaction would be forced to go backwards as well. So you need to supply enough push to basically cause them to reverse, because obviously this wants to release electrons, this wants to eat them, but in order to charge it back up after a period of time, once all of this is converted to this, we need to provide enough push to cause them to go back. So the advantage of the rechargeable batteries, as I said, sort of the environmental ones, you don't have as much landfill problems, and also just in terms of cost, and you don't need to go sort of looking to extract all these metals from somewhere if you can use them for longer. Okay, so the final one we look at now is the fuel cells. Okay, so the final one, so this is the fuel cell. So the main advantages of this one, there's no pollutants in terms of toxic pollutants, carbon dioxide, things like that given off. The only product which we are getting from this, as you can see down here, is water, so that's fairly safe. It can be continuously filled, so it's not like having to recharge the batteries or get new batteries. All it does is pump in some more hydrogen and oxygen and it can continue going. Some disadvantages of that: cost of hydrogen, so in terms of actually producing it. It's not entirely carbon neutral either, because despite the fact we're not getting any carbon given off here, then you've still got sort of a carbon factor to take into account when we're actually producing the hydrogen in, say, factories, things like that. So I wouldn't really classify it as carbon neutral. And you've also got the risk of obviously transporting about large amounts of hydrogen, storing hydrogen, and the risk that it could explode. So a couple of advantages and disadvantages there. So the cells set up in sort of the standard way. We've got some platinum electrodes here. We've got potassium hydroxide there, just acting as our electrolytes, just to give us K plus and OH minus, same as the salt bridge was acting earlier. And as we can see here, these are our half equations for it. So as you can see, 0.4 for the oxygen actually taking the electrons. So the oxygen gets reduced, it acts as an oxidizing agent, causes the hydrogen to be oxidized into water and to release the electrons. So if I want to work out the electromotive force, then more positive take away the less positive, gives us a value of 1.23 volts. So it's not particularly great in effect. We also, the rate of this is so slow as well, with having to get hydrogen to react with oxygen. There's a fairly high activation energy there, because obviously they're not reacting in the air what you're breathing in now, otherwise you'd be in trouble. So in the engine, they do have to do it at a higher temperature, and as we mentioned earlier, higher temperature tends to reduce this value. So it's countered a little bit in terms of using higher pressure as well to kind of keep trying to push that reaction forward to counteract the fact that temperature would be trying to reduce this. Now, one of the questions which I've seen asked, obviously we can see here we are doing this under alkaline conditions. It's asking you to predict sort of what the electromotive force would be under acidic conditions. If you looked at the two half equations for acidic conditions and then combine them together, just the same as I've done here. So obviously reactant, reactants, go to product and product, and then I've just cancelled some things out. If you did that for the acidic conditions, your overall reaction comes out the same. So if your overall reaction is the same, then your electromotive force would also be the same. And that is it for redox equilibria. Thank you.